So today we are presenting on pressure drop in packed bed reactors. So a bit of an introduction, what is meant by packed bed reactors? PBRs consist of a cylindrical shell with convex heads. Most are vertical and allow reactants to flow by gravity. Inside these reactor, there's a fixed bed of catalyst, and normally packed bed reactors are heterogeneous reaction systems. The purpose of these is to typically improve the contact between two phases in chemical or similar process. You can see this on the diagram below of a PBR. And in the following table, we can see two different present phases. We can have a gas phase solid catalyzed or gas solid reactions. Again, PBRs are typically used in heterogeneous gas phase reactions with a catalyst. And then we have the advantages and disadvantages. So for the advantages, we have high conversion per unit mass of catalyst. We also have low construction, operation, and maintenance cost. And again, this is a continuous operation. We also get the possibility of more contact between the reactant and the catalyst, and thus we get more product being formed. And this also works effectively at high pressures and temperatures. The disadvantages are first that the temperature can be hard to control in such system, and we can get also undesired thermal gradients and or channeling of gas stream can occur. And finally, the PBR may be difficult to service and clean. And so to understand the effect of pressure drop, we first have to understand what exactly is pressure drop. And pressure drop is a term used to characterize the reduction in air pressure from the compressor discharge to the actual point of use. So pressure drop occurs as the compressed air travels through the treatment and distribution system. In liquid phase reactions, the concentration of reactants is insignificantly affected by even relative large changes in total pressure, and so the effect of pressure drop can be ignored. However, in gas phase reactions, the concentration of reacting species is proportional to the total pressure, and therefore the effect of pressure drop can be key to a reactor's operation. And so what really happens is as pressure decreases through the length of the reactor and thus the volumetric flow rate increases, this results in the concentration of the reactant to decrease in addition to the decrease already from the conversion. And then at the end, the result is that there's going to be a decrease of the rate of reaction. So the pressure drop as a function of the reactor length is quantified by the Argon equation and will be described in the next section.
Okay, so now let's look into how we can mathematically determine how this pressure drop will affect things like the conversion in the reactor and the amount of catalyst weight required. And so we can look at the most simple reaction that we have. A goes to B in the gas phase because we know that pressure effects are only going to really matter for gas phase reactions. And so for a packed bed reactor, we know we can write the overall mole balance, dFA dW, is going to equal RA prime or minus K1 prime Ca in this case. And we can make our normal substitutions to get everything in terms of conversion. Fa is equal to Fa naught times 1 minus x, and we know the volumetric flow rate ratio is 1 over 1 plus epsilon x times P over P naught times T naught over T. And so we make those substitutions in, we'll get a final mole balance that looks like dx dW is K1 prime Ca naught 1 minus x divided by Fa naught 1 plus epsilon x times P over P naught times T naught over T. And we have talked a lot about how to deal with the T naught over T in non-isothermal operation, but we haven't done too many examples looking at how to deal with the P over P naught when it's not isobaric. And so we're going to look into that now and how we would incorporate a P over P naught expression to solve the conversion over the catalyst weight. Okay, so we're going to start with an equation from the text. It's called the Ergun equation, which is equation 5-22. This equation relates to change in pressure down the change in the length of the reactor. And we know most of the terms in this equation. For example, this is the density, this is the gravitational constant, and this is the particle diameter. Then we have the porosity or the void fraction and viscosity of the gas. The only thing that might be new here is this G term, which is just defined as the density times the velocity at the entrance conditions, which is the mass, it's in units of mass divided by length squared times time. Okay, so the first thing we might want to account for in this equation is the fact that the density itself is also changing as pressure changes. So we can use the fact that at steady state, we have a constant mass flow rate, which could be written that mass flow rate initially is equal to the mass flow rate anywhere down the length of the PBR. We know the mass flow rate is the density times the volumetric flow rate. And so we can get an expression for density is the initial density times V naught over V. And what do we know about V naught over V? Well, that's going to be density times, or divided by 1 plus epsilon x times P over P naught times T naught over T from the expression that we had above. And so we can actually plug this in to equation 522 and get a new expression that accounts for the density changing with pressure. I'm going to go ahead and paste it again. And if we plug in for the density, this expression above, this will just change to rho naught. And then we're going to have to multiply by 1 plus epsilon x times P naught over P times T over T naught. You'll see everything flips because the density was in the denominator of this equation. Okay. Now what they've done in the book is just called this whole constant here beta naught, which is in units of pressure per length. This is helpful, it helps simplify the equation down. So now it's just going to look like dP dL is minus beta naught times 1 plus epsilon x times P naught over P times T over T naught. Okay, and the only problem with this equation is that it's in terms of the reactor length and not the weight of catalyst. This is what we desire. That's what our mole balance was in terms of. And so let's do that. We know the weight of the catalyst is going to be the volume of the catalyst times the density of the catalyst. And we know the volume of the catalyst is going to equal the cross-sectional area times the length of the PBR. But then we're also going to have to multiply by 1 minus the porosity, because the whole entire packed bed reactor isn't full of catalyst. We have to multiply by 1 minus the porosity to get the fraction of the volume that is full of catalyst. Okay, now we can get that the length is the weight divided by AC 1 minus the porosity rho C, and go ahead and plug that in for L. So we have dP dW divided by AC 1 minus the porosity rho C is minus beta naught 1 plus epsilon x times P naught over P times T over T naught. Okay? And then if we pull that out of the derivative and move it to the other side, we'll get dP dW is minus beta naught divided by AC times 1 minus the porosity rho C is times 1 plus epsilon x times P naught over P times T over T naught. And to get this to match like the book expression, what they have done is they actually multiply the top and the bottom of this equation here by 2. So let me do that. So they multiplied this by 2, and so you got to put a 2 in the bottom, and I'll put the minus sign back. And then you also they also multiplied P naught down here, which means we want to divide this term by P naught to keep everything consistent. Okay, and what they have done is called this constant here. This whole constant is called alpha. which is just has units of a mass to the -1. And they've defined a lowercase p as p divided by p naught, okay? So if we rewrite this with those simplifications, we'll get dp dw is minus alpha divided by 2 lowercase p, 1 plus epsilon x times p naught times t over t naught, okay? And then we can divide the p naught over and we'll get dp over p naught is divided by dw is this 1 plus epsilon x t over t naught, okay? And we know p over p naught, really. We can erase this and just call that d lowercase p. And this is the final expression for that. Okay, so this would be pretty hard to, or you could solve it using something like polymath, but it'd be pretty hard to implement with the dx dw expression that we've derived here because they're coupled differential equations and t itself depends on x if it's not isothermal. But if we have a simpler case maybe where epsilon is equal to 0 and it is isothermal, that will simplify our math a lot. So then in that case, our expression would look just dp dw is minus alpha divided by 2 lowercase p. The other terms would go away. And if we cross multiply, we can get 2p dp is minus alpha dw. Then we integrate from 1 to p and from 0 to w. Take note that it's from 1 to p because p, which is p over p naught, initially would be p naught over p naught, and so you'd get 1 there, not 0. So when we integrate that, we're going to get p squared from 1 to p is equal to minus alpha w. And that just means that that's just going to be p squared minus 1 is minus alpha w. Or lowercase p is going to equal 1 minus alpha w raised to the 1/2. And that expression will be much easier to implement using something like Euler's method with the mole balance, which we will talk more about in the next example.
Now solving the example for a pressure drop in a PBr catalytic reactor. The hydrodemethylation of toluene is to be carried out in a PBr catalytic reactor. The molar feed rate of toluene to the reactor is 50 moles per minute. The reactor inlet is at 40 atm and 640 degrees Celsius. The feed consists of 30% toluene, 45% hydrogen, and 25% inerts. The hydrogen is used in excess to help prevent coking. The pressure drop perimeter alpha is 9.8 times 10 to negative 5 kilograms to negative 1. They want us to plot and analyze the conversion, pressure ratio, and the partial pressures as a function of PBr catalyst weight. The rate was also given to us in example 10-1, along with the values of K, KB, and KT. Starting off with the mole balance of a PBr reactor, we know that dF of T over dW is equal to the rate of toluene. We also know that F of T is going to be equal to F of T naught, 1 minus x. If we take derivative of both sides, dF of T equals negative F of T naught dx. Plugging that back into the equation, we see that dx dW is equal to negative rate of toluene over F of T naught. Next, we want to find the rate law, which is given to us right here, so I'm not going to rewrite that. And then step 3 is going to be the stoichiometry. The concentration for a gas reaction is going to be equal to the initial concentration minus the concentration of toluene over the coefficients ratio times x over 1 plus epsilon x times p over p naught times t naught over t. It is isothermal, so this t naught over t is going to be equal to 1. And this ratio for pressure right here is going to be equal to our pressure ratio, little lowercase p. We also know that the pressure of toluene is going to be equal to the concentration of toluene times R times T. And plugging in the equation above, we're going to find that Ct naught times 1 minus x over 1 plus epsilon x times the pressure ratio times R times T naught is going to be equal to the pressure of toluene. We also know that Ct naught times R times T naught is going to be equal to the initial pressure of toluene. We also know that epsilon is equal to the coefficient of, or the amount of toluene times the change in moles of gas over the coefficient of toluene. The moles of gas is 0, which is going to be meaning that epsilon is going to be equal to 0 from right here. Plugging those two things back into the pressure of toluene, we can see that the pressure of toluene is going to be equal to the pressure initial of toluene times 1 minus x times the pressure ratio. Now solving for the pressure of hydrogen, it's going to be the same type of equation, except it's going to use omega of hydrogen right there instead of the 1. Omega of hydrogen is going to be equal to the amount initial of hydrogen over the amount of toluene initial, which we can see right here. Toluene is 0.3, where hydrogen is 0.45. Plugging that in, you can see that 0.45 over 0.3 is equal to 1.5. Therefore, the pressure of hydrogen is equal to the initial pressure of toluene times 1.5 minus x times the pressure drop. Now the pressure of benzene, which is a product, is going to be equal to Pt naught times x times the pressure ratio. That is because it is a product, so it's just dependent on the conversion. Now because epsilon is equal to 0, we can use the integrated form of pressure drop term, which is equal to P over P naught, which is equal to 1 minus alpha times the weight to the 1/2. Now we must calculate the maximum catalyst weight. To do this, we need to say that the exiting pressure must not be less than the atmospheric pressure. Therefore, Pt is going to be greater than or equal to 1 atmosphere. We also know from the prompt that Pt naught is equal to 40 atmosphere. Plugging that into the equation right there, 1 over 40 is going to be equal to 1 minus 9.8 times 10 to the negative 5 times weight to the 1/2. This gives us a weight of 10,197 kilograms. Therefore, when we solve, which is step 4, we're going to use Excel to do Euler's method up to 10,000 kilograms. So now solving this problem in Excel, I placed all the given values right there, and I chose my change in weight to be 10. I then filled out this first row, and I know that the weight initially is 0, my pressure of toluene initially is 12, my pressure of hydrogen is the 40 times 0.45, which is equal to 18, and I have no pressure in benzene because the reaction has not occurred yet. I then went through column A and filled out the weights, which is going to be equal to the row above plus the change in weight. And I dragged that down to 10,000 kilograms. Then I solved for the pressure drop, which is going to be 1 minus alpha times the weight to the 1/2. Since I have the weights all filled out, I can also fill this row out, this column out. I did that right there. Then I know the rate of reaction equation, so I filled that out right here. All these values are going to be constant, and these values are going to be changing per row or per weight. Therefore, I cannot fill in the rest of this column because I do not know the values of these columns right here. Next, I solved for the conversion, and initially the conversion is 0 because the reaction has not occurred yet. And right here, given this delta x equation, I can solve for the x at 10 kilograms because it's going to be the row above minus RT divided by FT naught times your change in weight. I also cannot drag this down because I do not know the reaction rate right here. Then I did my partial pressures, which are going to be given by the equation right here. This is going to be PT. This will be the pressure of H, or hydrogen. This is going to be the pressure of benzene. And all these are determined off of PT naught, which is going to be this value right here. And it will not change for each row and column. Now I can fill it in because I have all these partial pressures right here. Fill that in. And now I can take this section of the row and drag it all the way down to 10,000 kilograms. I can then plot it to see how the partial pressures and the conversion affects everything. So as my pressure drops, my conversion is going to be increasing, and it's going to end about a 0.68 conversion. Also, when I plot my partial pressures, my pH and my PT tend to decrease at the same slope until the very end. It starts to differ right there, and my partial pressure of benzene increases and then goes back to decreasing. At the very end, my pressure of hydrogen and my pressure of benzene are very close and seem to be similar, but there is a slight difference right there. Now what if there's no pressure drop? Then this whole column is going to be equal to 1, and I did that right here. When I compare the conversions, without a pressure drop, or this orange line, is going to be ending up at about 0.8. So without, or with a pressure drop, is going to be 0.7. Without a pressure drop is going to be 0.8. That's about a 0.1 conversion, and 10% of the conversion is going to change. This shows that utilizing the pressure drop and accounting for it makes a big difference on the conversion.
Finally, in conclusion, we want to know, how does the pressure drop affect conversion? And this is how it does it. So when the volumetric flow rate goes up, conversion goes down for both with and without pressure drop. Conversion is less with pressure drop than in the case when the pressure difference is equal to 0. When K increases, the effect of the difference in pressure on conversion is much more pronounced, and this is also in the case of increasing the initial concentration of species A. When alpha goes up, the difference in pressure also goes up, and the conversion is less for the same catalytic bed. And so, why is pressure drop in a packed bed reactor important? First of all, ignoring such a pressure drop could end up with unexpected reactor performances. And pressure drop, as we know, is an important parameter economically in many chemical processes. You can see some of the examples of some processes that need or use PBRs on the table below. This pressure drop is important as it directly dictates the operation cost of the pump or of a compressor. And by determining how much pressure drop each part causes, you can calculate how much pressure you need to run your full process. So the lower the total pressure drop of a system, the less gas is needed to run it. And this saves a lot of companies so much money. Finally, our last slide. So for the overall importance and understanding of why we use PBRs and why we account for a pressure drop is that first, we prefer PBRs because it's a simpler technology, it's easy to operate, and it gives us a higher conversion per weight of catalyst compared to other catalytic reactors. On the understanding of it, it's that understanding how to calculate pressure drop in packed bed reactors allows engineers to properly design a system and thus determine variables such as, again, size, diameter, among other things. Pressure drop should be taken into consideration when assessing optimal reactor and catalyst pellet sizes for any process, just because it is super important and it affects a system in general. And well, thank you for listening, and I hope you enjoyed the video.